Hi, it's Miss Molesbury here. This video, we're going to keep building on our knowledge of inverse functions. So it's day 2. You may decide that you want to try these problems on your own and then just kind of check with the key. Maybe you want to watch the video faster speed or try some of them on your own, pause the video, and then check back in. Because really, we did cover a lot of this last class. And of course, it is a review from Algebra 2. So let's go ahead and dive in. We're talking about inverse functions again. And it says, if f and g are inverse functions, then g of x is equal to the inverse of f. So there's your inverse notation. There we go. I guess I'll go ahead and label that. And then we know that for an inverse, if x comma y is a point on the graph of f of x, then y comma x is a point on the graph of g of x, which we said was its inverse. So we switch the x and y value, the input and output. 3 says with inverse functions, all of the x and y values are switched, so the graphical behaviors in terms of x and y will also be switched. For example, it probably makes you think the domain of the original function becomes the range of the inverse, and vice versa. The range of the original function becomes the domain of the inverse. We're going to see that come up in several questions today. And then number 4 says a continuous, so picture a continuous function, no breaks in the graph. It will only have an inverse function if it is strictly increasing or strictly decreasing. So meaning it can't change direction, so it'll have no extrema. Okay, so if a function changes from increasing to decreasing or vice versa, it will no longer pass the horizontal line test, and its inverse relation will not pass the vertical line test as a result. So what we kind of touched on last class is we said, for example, if we talk about a function, I know we did this as the example last time, but if we say f of x is x squared, right, this function doesn't pass the horizontal line test. So even though it definitely is a function, it passes the vertical line test because it has y values here that repeat. When I go and switch those x and y's, it's going to have x values that then repeat. So that's why we then have to restrict the domain. So for example, if I provide only the right side of that function, so meaning all of the x's greater than or equal to 0, as I go and change all of those ordered pairs, it would give me values like, drawing my graph here, it would still have 0, 0. It would give me the 0.1, 1. It would give me the 0.4, comma 2, 9, comma 3, right? And would just make the positive square root of x. If we had the negative square root of x, then that's its reflection over the x-axis, and that corresponds to the left side of the quadratic function. So the point here, though, let's go back to the point. We need to have a function that is strictly increasing or strictly decreasing to make sure that it will have an inverse function. So its inverse is a function. Okay, so I'll bring it up when it comes up. Last class, we did a lot of finding the inverse equation, and we're not doing that today. Instead, it's going to look a lot like your composition AOL or your Big Ten practice that we did, 2.7. We're going to do composition with a mixture of inverse functions. So it says, let f be a continuous function with selected values in the table below or above. Oops. Let g be the inverse of f such that g of x is equal to the inverse of f of x. Find the following values if possible. Okay, so here's the table for f of x. I'm going to quickly glance and see that it is strictly decreasing. It's continuous. The y values continuous because the problem told me so, and I see the y values are constantly decreasing. Suggestion is that you could go ahead and make a table for the inverse by simply switching the x's and the y's. So the point -3, 6 becomes 6, -3, and I'm literally just going to take a second to switch every ordered pair from the first table. And you can decide if you need this or not. I'm going to refer to it, but I'll tell you, of course, how you could not use it if you choose. Okay, so the first part says composition. I don't see an inverse here at all, so let's start on the inside. F of 0, I'm going to look at function f of x. F of 0 is 1. And so I'm going to replace this and make it f of 1. Using my table again, when the input is 1, the output is -1. And that is the overall answer once I evaluate this composition. I'm going to go ahead and box it just to show you, but remember on the AP test, we may not always want to be boxing our answers because that means they won't grade the rest of your work. Okay, so on B says g of -3. And if you're like, wait, there's no function g. Well, yes, there is. It told us that g of x is equal to the inverse of f. So this is asking me to do the inverse of -3. So since you made a table, you could just go look at your inverse table. When the input is -3, I get a 4, and I'm done. So I chose to look at the input of -3 in the inverse table. Now, you could also, if you don't make an inverse table, you could go look at the output of -3 on the f of x table. So when the y of f of x is -3, its x is 4. If that's confusing to you, just switch the points and then refer to the table listed. So g of 6, that means we're going to be looking at the inverse table when the input is 6, and that corresponds to -3. G of -1, so start on the inside, right? So this is the same as doing the inverse of f at -1. So starting here, I'm going to look at my inverse table. When -1 is the input, 1 is the output. And from there, I'm going to look when 1 is the input of my inverse, I get 0. So 0 would be our final answer there. The next one, make sure you're starting close to that input value. We're going to do f of -2 and then find the inverse of that value. So f of -2 is 3. And then we're going to find the inverse when the input is 3. So I'm going to check now my inverse table. Input of 3 goes with -2 for my output. And then last one, pretty simple, just says the inverse of f of x when x is -3, or the inverse of -3 here. So check your table. We're able to find that. It is 4. Okay, so very similar to what you did on your 2.7 compositions. If you make an inverse table first, then they can be really straightforward, just like that. Okay, let's look at a graphical example. Example 2 says the function k is defined over the interval from -4 to 11 as shown in the graph above. Let the inverse of k of x represent the inverse of k. We're going to graph it on the axis above. What is the minimum value, the maximum value? So let's go ahead and look at the graph. My suggestion here, at least for my brain, I'm going to have to take some ordered pairs from the original function and then switch them before I plot this. So I'm going to pick the endpoints, so -4 and -3, and then anytime that the rate of change changes. So I'm going to pick the point for -1, 6, 4 here, and then the other endpoint 11, 6. So then for the inverse, I'm going to go ahead and change the x and y's, just switch them. Inputs become the outputs. And then let's go plot those points. So -3, -4 is a new endpoint. -1, +4, and I'm going to connect these as I go. If you don't do that, you may end up with 4 random points on your graph and forget, like, what shape is this making? For 6, there we go. And last but not least, 6, 11, which doesn't quite fit on our graph, but just kind of give it an estimate. There we go. And so you can double check yourself, look for that symmetry about y = x, the linear parent function. So if you kind of want to draw that dashed line there, just as a way to see that the functions are equidistant from the linear parent function. Okay, so we graphed it on the axis above. It says, what is the minimum value of k of x, the original? So this is asking for the smallest y value, right? Which would be -4. And then it asks the minimum value of the inverse. So if, oh, hang on, I just realized I answered it for the inverse. Undo. My apologies. So the minimum value, I was looking at the wrong function, of the original graph, it only goes to -3. That would be its smallest y value. And then the minimum value of the inverse is going to be -4, which it should not be a surprise, right? The domain of k, which was -4 to 11, is going to become the range of k of x, the inverse of k. So the range is going to be from -4 to 11 for the inverse. Okay, then it asks us to focus on the inverse and evaluate the inverse at 6 and the inverse at 4. And those are actual values that we put in our table already. If you did not graph the new function, remember these are y values on the original function. So you could go to the y of 6 and look at the original function and see, okay, well, the original function, that corresponds with 11. But again, it's going to be easier if you go ahead and make an inverse table so that you can just quickly look and see the inverse at 6 is 11 and at 4 is 6. Just using these values from the table. Okay, so let's do some more. Example 3, looking similar at first glance, the function f is defined over the interval from -2 to 8, as shown in the graph of f above. Let the inverse of f represent the inverse, okay, graph the inverse on the axis above. So same thing. I'm going to use those endpoints for sure. -2, 7, 2, 3, 4, -1, 8, -3, and then for the inverse, using that inverse notation, and we'll just switch the inputs and the outputs. Oh, notice that these graphs, like this one, has been strictly decreasing, even though it's decreasing at different rates. Same thing for the one up here. It was increasing always, even though the rate of change was different, and it would pass the horizontal and vertical line test, the original function. Forgot to mention that on the last one. Okay, so plot these new points, 7, -2, 3, 2. I'm going to go ahead and connect that. If you're unsure on certain things too, like, oh, should I have made the x-intercept at 5? We'll go check and see. If the y-intercept is 0, 5, right, then the x-intercept here is going to be 5, 0. So if you're unsure, you can always use more points. -1, 4. And then, let's see, -3, 8. Okay, so looks kind of funky, but remember you can check your symmetry by drawing your y equals x. See how I did here in the middle? Pretty close. Okay, so now what is the maximum value of the inverse? So you have two options. You can look at your graph and see that the highest y value here is 8. So the maximum of the inverse is 8. That's the largest y value. But remember, what that means is that is also the maximum x value for the original f of x. So the maximum y of the inverse was the maximum x for the original. It wants us to evaluate at two different inputs. So we're looking at the inverse. Our input is 3. That's one that's in our table and graph. It equals 2. If my input is 1, we'll see. My graph says 1, 3. Graphically, that's what I see. But what we can do is we can check when y is 3 on f of x. So I would take the y value of 3 and I'd go look and see, oh yeah, that was actually the point the point there. Oh, never, wait, when y equals 3. Oh, I'm sorry, what am I saying? Hang on, let's change it just a second. Not when y equals 3 on the inverse. Let's say when y equals 1, right? So if we were talking about the inverse, that x value there was the y value on the original function. So going to where y is 1 and following it over to the function, I can see that it had the ordered pair 3, 1, which did become 1, 3 on the inverse. Okay, my apologies. On C, it says, what is the domain of the inverse? You can either look at the graph, or if you didn't want to take the time to sketch it, if you're doing a multiple choice problem on a time crunch, it's going to be the same as the range of the original function. And that range was from -3 up to 7. So I answered it based on the range of the original, or go look and see -3 to 7. Yep, that's the domain of the inverse. Based on the endpoints, that would be a faster way to check. Okay, very last question is going to incorporate different functions. We have G, which is a table, I guess, or a graph. Let's just read the problem and see. The function g is defined over the interval where x is between -3 and 10, as shown above. Let g -1, so represent the inverse of g. Values of the increasing function h are given in the table above for selected values of x. Find the following if possible. Okay, so it gives you tables because the goal of this lesson was to see, can you do this on your own? So we're suggesting you go ahead and fill out these inverse tables. So I'm going to take a second to do that. Okay, great. I just went and switched all the x's and y's. And then it's going to take a second longer for function g because I'm taking the ordered pairs from the table. So -3, 6 is going to become 6, -3. It looks like there's only 1, 2, 3, 4. If I include the endpoints and the points where the function is changing its rate of change, I only have 4, and there's 6 here. So I'm going to also choose the intercepts as my other 2 points to put on the table. So 0, 5 for the inverse will become 5, 0. 3, 4 will become 4, 3. 6, 1 will become 1, 6. 8, 0 becomes 0, 8. And 10, -1 becomes -1, 10. Okay, great. Now we're just evaluating these functions again. So just be careful. Start on the inside. So g of h of 6, we'll start by finding h of 6. Function h, input of 6, gives me an output of 10. And g of 10, looking at function g, when x is 10, y is -1. That's it. B says the inverse of g of h of 0. So start with h of 0, meaning we're going to look at this table. H of 0 is 3, so that becomes our input in the inverse of g. I'm going to look at the table where we switched these points. Oh, wow, okay. I don't have that on my table. So I'm going to go to the graph and see if I'm looking at the inverse, right? It would be the y value of g. When is that? 3? So I see it had the ordered pair 4, 3. So that must mean that on the inverse has the point 3, 4. It also has the point 4, 3, which is kind of interesting, but not the point we're looking for. So I'm going to get 4 here. C says we're going to do the inverse of h of g of 8. So starting with the g of 8, I'm going to look at the table, the graph provided. G of 8 is 0. And then when the input of the inverse of h is 0, I get -1. And last question, the inverse of h of the inverse of g of -1. Exciting. So I'm going to look at the inverse of g of x. The input here is -1, so I'm going to get a 10. And then if 10 becomes the input on my inverse function, the output is 6. So even though it can seem like an extra step, really creating these tables can be really helpful. That way you don't have to keep going back. Am I thinking about an x or a y? You basically have exactly which function you should be looking at, and then you think of all of these values as inputs in that function. So hopefully this was helpful, good extra practice. Make sure you go back and do the first DP over 2.8 if you haven't yet. All of it can be assessed. So today was more focused on evaluating and making sure we have our notations down, and still working on understanding the relationship between between a function and its inverse. So please let your teacher know if you have any questions.